She's a former chair of the Polar Research Board of the US National Academy of Sciences and is currently president of the American Geophysical Union's Global Environmental Change section and also president of the Quaternary Division of the Geological Society of America. And I think she's going to tell us all about what we can learn from the past about potential future warm periods and hazards that might be facing us in the not too distant future.
Thank you, Jonathan. So we'll go to my first slide, and it's my role to provide some background on what paleoclimate tells us about the situation we're in now. So could we please go to the next slide? The important urgency of now could not be overstated. We have a responsibility to future generations. We need to focus on the delayed but certain and irreversible climate impacts that we face. The geologic record tells us that sea level rise is inevitable from the large ice sheets in a warmer world. So this past really does inform our present and our future, because we know and understand better the sensitivity of these ice sheets to temperature rise. And so today's temperature rise is faster than ever, and we can expect the impacts to also be faster than ever. Next slide, please. Skip that one. So the Earth can warm in several ways. If you go 2 clicks, please. The Earth can warm through orbital changes, the shape of the Earth's orbit around the sun. But that really doesn't matter because it happens on very, very long timescales of tens of thousands of years. But the second way that we can warm the planet is really through greenhouse gases. And here you see a record of the ice core fossil air preserved in bubbles from ice cores from Antarctica. And you see that over the last 800,000 years, the normal range is between 180, 280, 180, 280 parts per mil. So we've been bouncing with glacial interglacial changes in that window of CO2 naturally. But if you click one more time, you'll see that we are actually in this box way outside the normal envelope of CO2 on the planet as we approach 420 parts per mil. Next slide, please. So one more click, and you'll see here is my family's timeline on the recent change. And you can see that since the time my grandmother was born in 1898, carbon dioxide in the atmosphere has gone from 295 parts per mil up to what it is today, again, approaching about 420 parts per mil. And you can see on there when my parents were born, when I was born, when my children is born, this is happening extremely fast. Next slide, please. So we're going to take a look at other time periods in the past very quickly when CO2 was about what it is today. So next click, please. We're going to take a look just at the recent time, and we'll go to the next slide, please. So here we are looking at the last 6,000 years of CO2 preserved in those ice cores. And on the top diagram, you see a very flat purple line running across. That is at around 270 to 280 parts per mil. And you see the huge uptick at the very end of the right-hand side of the slide. That is the last 100 years. And underneath it is a figure that shows you the impact of fossil fuels parallel with that increase in CO2. There's no question about the source of changes in our atmosphere and how extreme it is, even in the last 6,000 years. Next slide, please. So here we see CO2 going down in the middle of the diagram to 180 during about 20,000 years ago. And if we click one more time in this figure, now the little uptick there is the last interglacial, 125,000 years ago, when sea level was higher than present, and CO2 was about 285 parts per mil. Let's go back again, another click. Okay, so now one more click, and we're going to go into the Pliocene. We're going to go back to 3 million years ago and take a look at what the CO2 was at that time and what was sea level. Next click. Next one. And the next slide, please. So if you click one more time, a red line will come up and show you that if you look at the left-hand part of this figure, at around 3 million years ago, the carbon dioxide in the atmosphere is measured by many groups of scientists to be in the range of 350 to 410 parts per mil. So we are already today beginning to go outside the envelope of what we think CO2 was like 3 million years ago, when we did not have a Greenland ice sheet and the West Antarctic ice sheet was waxing and waning in a dynamic fashion, giving us an idea of the sensitivity of the ice sheets to this very high CO2 level. Next slide, please. This figure shows you 4 different periods. Today, on the left, 1890, pre-industrial, and the next, last interglacial, a strong interglacial around 400,000 years ago, and on the right, 3 million years ago. And it gives you an idea of the intensity of sea level rise. And you can see that today, being in the last few years, hovering at around 400 parts per mil, we've approached what is the Pliocene CO2 level. And this implies that we are driving the planet toward a sea level rise eventually could be as much as 15 meters or almost 50 feet above present. So we can slow this down by decreasing CO2 and decreasing the rate of sea level rise. Next slide, please. So now let's go back one more click, and we're going to head now back into even farther back in geologic time, 55 million years ago. Next slide, to a time called the PETM, or the Paleocene Eocene Thermal Maximum. At this time, there was massive volcanism, we think, number of different reasons. CO2 and methane in the atmosphere increased dramatically, causing massive ocean acidification, mass extinction in our surface oceans that took almost 50 to 100,000 years for us to overcome. And this rate of change in CO2 in the atmosphere 55 million years ago took about 10 to 20,000 years to show. That's the blue line giving you a time frame here. But what's important to understand is today we are increasing CO2 10 times that rate, 10 times what we think we observed 55 million years ago. Next slide, please. And so we need to think about where we're headed. If we don't change the CO2 in the atmosphere, we just keep doing what we're doing, it's, if you go one more click, you can see that we will actually be approaching, within about 200 years, the level of the PETM. We will be approaching that level of CO2. And remember, 200 years from now, that's not very long when you think about what we've done to the planet since my grandmother was born. Next slide. So this figure shows you a projection in about 280 years from now, what the Greenland ice sheet thinning might be. This ice sheet has 6 meters of sea level. And so we can see that we do not want to be committed to this type of sea level rise in the future as we watch these ice sheets accelerate under a warming world. Next slide, please. My last one. So I think it's really important that we have a responsibility to future generations to slow down the warming and avoid rapid change. The geologic record tells us that sea level rise from especially large ice sheets is driven by temperature. And the past informs the future. We can't afford to ignore it. Thank you very much.